So I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class, this opportunity we have to study your creation together. I just pray that you'd guide our steps today, help us to understand a little bit more about linear algebra today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get into it. So we want to talk about matrices and their operations, and perhaps more importantly, a notational scheme that allows us to make really nice, efficient arguments about them without much trouble. So let's start at the beginning here, as soon as I find my markers. Did I ever press record? I did, right? Okay, cool. Is it bouncing, like the audio bar? La la la. All right, good. So, the matrices. Now, if we have, we say A is an element of R m by n, where R is a commutative ring. So what I mean by that is really just that, and if you look at my definition 1.11 on page 2, I'm a little bit even more cagey than that. I just talk about a matrix formed with objects from a set. Maybe I should do that here. Let me do that. Sorry guys, I'm already. So let S be a set. All right. So that's even less structure, right? But a matrix is an array, right? So it looks like this: A11, A12, A1n, AM1, AM2, AMN. All right. So here, sometimes we use this abbreviated notation like AIJ, like this, with the brackets around it to indicate the collection of AIJ. Now here we have 1 less than or equal to I, less than or equal to M, 1 less than or equal to J, less than or equal to N. So I, of course, is the row index in this current context, and J is the column index in the current context. Now those are not sacrosanct. Like, we can use I and J. Just because it's I doesn't mean it's a row index. Just because it's J doesn't mean it's a column index. They get used in both places depending on the equation, right? Like I'm saying, those notations are not reserved. But this is a matrix. It's an array, m by n array. Now, of course, you can talk about, like, you know, for example, this, if we just look at these, that's like column 1 of A, right? That would be column 1 of A. If we just looked at these, right, that would be row what? Row M of A, right? So this would be technically an element of S. There's one row by n columns, and column 1 would be an element of S m by 1, because there's m rows in one column. Okay? And here's the definition. If we calculate the jth column of A, the ith component of that, what is that? Well, that's Aij, right? If we calculate the ith row of A, the jth component of that, that's Aij. You notice the juxtaposition of the letters here to make that happen. All right. Any matrix can be looked at as like a stack of column vectors glued together, so it's a concatenation of its columns, or as a stack of row vectors, right? So we can think about a matrix as being rows or columns glued together. Now, of course, you could ask, like, what is a matrix actually, but, well, I don't know, you can, if you're interested in that, we can talk about it in office hours, I suppose. But there is a way of rigorously constructing such objects from set theory, if you're interested in that. But if we went into that in detail in class, it would not help us even a slight, even a tiny bit in anything that followed, all right? So, like, I'm not going to do that. I used to get, like, really wrapped up in those kinds of questions, like, but what is it? You know, it's an array, but how do you define an array? Well, with set theory. Okay, well, good. Maybe that should be a homework problem, I guess, but I guess I probably don't even care about it enough to make it a homework problem at the moment. And, oh man, that's really, that marker, very dry. Goodness gracious, it's hardly coming off. So what does it take for two matrices to be equals? The next question. Do you guys know?
For all I and j, every component is equal.
Right, for every component. So every component has to be equal. Matching components have to be equal, right? So to even ask the question, they have to be the same size, right? A and B in S m by n are equal if and only if, like, Aij equals to Bij, right? For all I and j. Now, if you'll forgive me, that's a slightly ambiguous kind of, like, for all ij, what do I mean by that? Well, that's a shorthand, right? That's a shorthand for this, right? In this context, like, let's let this understand for the sake of making me, I mean, in your homework, I'd like you to be more precise, but, like, for class board work, sometimes we're just going to do this for all ij. All right, so well, what kind of objects are in a matrix? Well, I've been very vague at the moment. It could be a lot of different things, right? You could have a matrix of real numbers, of course. That's mostly what we do. Matrix of rational numbers. You have a matrix of functions, right? You could have a matrix of matrices. Really, your options are unlimited in terms of what you could think about. One thing we can do, though, no matter where, like, this is another thing we can do for arbitrary matrices. If we have A in an m by n matrix, then A transpose is an element of Sn by m, where A transpose Ij is by definition Aj, right? And that suffices to define it, right? Because of our notion of equality I have right above, right? It suffices to define the ijth component. That defines the matrix, because two matrices are equal if they have all matching components. So that stands to reason that's enough to define the transpose. All right. What else can I tell you? So theorem, right? If we have column I of A and we transpose it, that's equal to what? Row I of what?
Just A.
I think I've messed up my theorem. So, sorry guys. Let me not. It's too. I'm a dummy. What I was trying for there was column I of A transpose. And how is that? Row I of what? You used to say A?
Yes.
Yeah. All right, so what's the proof of that look like? So here we go. Column I of A transpose, right? Let's calculate the jth component of that. So that's what? A transpose, what? How do we calculate the jth component of the ith column? Notice here. But I have to deal with the fact that the indices are swapped, right? So I don't put A transpose ij, I put A transpose what? ji, right? So this is by definition of column. And then next step, this is A ij. That's definition of transpose, right? And then what? Well, aij, remember, is row ia, the jth component, right? It's the ith row of A, the jth component. Definition of row, right? Now look at what we have. We have that the jth component of this column vector is the jth component. Well, I mean, we have these two these two vectors, right? They have the same components for each j. This holds for all j, so therefore what? In this context, j would be equal to what? Like, I guess it depends on where A is from, right? But if we're supposing that A is in Sm by n for the sake of discussion, that would mean that I ranges from 1 to m, and j then ranges from 1 to n, I believe. Therefore, column I of A transpose is equal to row I of A. And there you go. That's an example of an index proof. Sorry, I haven't started. This is not the easiest example either. I probably should show you guys like a less annoying example of index proofs than this, right? This isn't the greatest one. This does bring me to one of my next notational signpost warnings, things you need to notice. So our definition, if we talk about Sn, that by definition is S n by 1. And so, like, in sort of the most natural notation, I guess, S1, S2, da da da, Sn, right? It's a column vector. Right? A column vector, but since we don't want to write column vectors all over the place, well, instead, our notation is to write this instead like this. So this, you could also say it's equal to the row vector transposed, if you like. But if I write just square brackets, that's a row, right? If I write parentheses, it's a column. That's our sneaky hidden column notation, all right? If you had Math 221 with me, this is old news to you, but for those of you who are not, maybe or maybe not, this is the way you guys are doing things, I don't know. But it's the way we're going to do things, so there you go. Now, so what can you do with matrices? Well, you guys know, right? This isn't your first experience with this. You well know we can add matrices, we can scalar multiply them, we can multiply them, all those things, right? So we should review those and make sure we understand the notation. And we should take a moment here to make definitions for all those things explicitly in terms of index notation. So definition, let R be a commutative ring with 1 in R. That's the context I want to work in. Now, you're like, hey, hold on, flag on the play. We haven't had abstract algebra yet. Why are you using abstract algebraic terminology? To try to seed your intuition with a meaning for those terms, right? But just in brief, in short, like, what is a commutative ring with unity? It's simply a set that has addition, it has multiplication, and that addition and multiplication satisfy the usual rules, like the distributive property, multiplication commutes. There's a number 1 times anything else is is anything else again, right? Like 1 times x is x again. So like what are examples of commutative rings with 1? Real numbers, rational numbers, you know, even integers. Wait a minute. Oops. Odd integers. Like 1's not in the even integers, right? But there are tons of things. Wait a minute. Is odd integers? Oh, I'm wrong. Odd integers are not a commutative ring with unity either, because like 3 plus 3 is 6, but 6 is an odd, so it's not closed inner addition, right? But anyway, there are lots of examples of commutative rings with unity. There are more interesting examples, like modular arithmetic, like z mod 3 or something. If we look at the integers with modular arithmetic, that's a commutative ring with unity. And the large story here is simply that R supports a notion of addition and multiplication. If that's the case, then we can also define addition and multiplication for matrices of such things. All right. So in your homework, you'll get to play a little bit with some examples which have not just real or rational inputs. We'll have a few examples here and there of like z mod 10 or 7 or whatever. Okay, more about that later, but let's focus on the main thing here. So if A and B are in m by n, Rm by n, and C is an element of R again, then A plus B, Ij, and C times A, Ij, how are those defined? Like, how do we define the sum of two matrices? Just component-wise, right? Like, this is Aij plus Bij, right? And this is C times Aij. So there you go. Like, that's the definition. So here's a very silly, basic proof. Let's make it a little bit more concrete so no one feels uneasy. Example, I haven't had example. I guess it's example 1. Suppose A and B are in R, m by n. So that's the real numbers, right? Then A plus B is equal to B plus A. Proof, right? How would we prove such a thing? Well, A plus B, Ij, by definition is what? A Ij plus Bij, right? And I write the reason over here. Definition of matrix addition, right? What's my next step? And why is that true?
Because it's a commutative ring, so addition commutes.
Right, addition commutes for real numbers, right? Just like you said. There's nothing especially special about this example being real numbers, right? We could just as well have R, a commutative ring, and we can make the same steps because that's a property of a commutative ring. But anyway, and then final step, this is B plus A, Ij. How do I know that? Well, that's the definition of matrix addition, right? Hence, A plus B is equal to B plus A, as the above holds for all I and j. There you go. This would have been a more reasonable first index proof to show you. Anything that messes with transpose. Okay, that's a good. I think that's a good theorem for us to have done today. But it's, you know, the definition of column will catch you off guard if you're not watching out for it. The way the indices work there, right? It's like something a little bit off-putting, unsettling about the way the indices flip. But it is what it is. All right, so let us move along. So you guys know the properties of matrix addition. I won't write everything down in the notes on the board. I do hope you'll read the notes. So like the less interesting parts I don't write on the board. You know it already, right? Addition's commutative, it's associative, scalar multiplication works like you'd expect, right? If I have a constant plus another constant and oh wait a minute, I'm already thinking about multiplication. Let me not put the cart before the horse in here. I guess one interesting thing. So today I forgot my phone of all days, so I lose track of what time it is, you know. One thing I should mention before I get to multiplication that's actually important is we can build any matrix from a sum of fundamental matrices, right? That's worth noticing. So, let me trust the plan. I think I just tried to skip like to the end of the chapter, which would be dumb. What's the zero matrix? Matrix with what? All zeros, right? Yeah. The zero matrix plus any matrix is the matrix again, right? We know that. Now, I should talk to you guys about the standard basis. Right, so to do that, we need to introduce this symbol, the Kronecker delta. The way this works is it's 1 if I is equal to j, and it's 0 if I is not equal to j, right? That's how that works. So, definition, and this is a reserved notation for us, all right? E sub I, little e sub I, is the ith standard basis element, right? E sub I. And to define a vector, so E sub I is an element of, again, and this R is going to continue to be a commutative ring with 1. If you like, you could just think of it as the real numbers, but it could be a lot of things. So this is an Rn, all right? Which again is Rn by 1, which I'm going to stop writing pretty soon, but wait a minute. Yeah. Is defined by E sub I, the jth component of it is Kronecker delta ij. All right. And the other thing I wanted to define while I'm at it is Eij is an element of Rmn. This is big Eij, all right? Is defined by Eij. Well, the kth component of that is Kronecker delta Ik, Kronecker delta JL. All right. So let me just show you some specific instances of this notation, and I'll be a little bit more concrete here for just a second to make sure I'm not losing anybody. But you know, if I have, let's say V in, you know, R3, what is this, example 2? Example 2. Then we can write V as, you know, V1, V2, V3, which we can rewrite as V1, E1 plus V2, E2 plus V3, E3, right? Because like this E1 is 1, 0, 0, this E2 is 0, 1, 0, and this E3 is 0, 0, 1. And if you scalar multiply the numbers V1, V2, and V3 into those vectors and add them together, you get back where you started, right? Any linear combination, any vector in R3 rather, can be written as a linear combination of the standard basis E1, E2, E3, right? If we had A in R2 by 2, right, then A would look like A11, A12, A21, A22, right? And I could rewrite that as A11 times 1, 0, 0, 0, plus A12, 0, 1, 0, 0, plus A21, 0, 0, 1, 0, plus A22 times 0, 0, 0, 1. But you see, what these are, respectively, are E11, E12, E21, and E22. So these right here are sometimes called the matrix units, which is somewhat unfortunate terminology because sometimes when we use the word unit, we're thinking of something with an inverse. Well, these are not invertible matrices, far from it. They're a matrix where every component's 0, except for 1, which is 1. Right? So they're quite far from invertible, but they are units in the sense they just have one element, which is 1. That's why they're called matrix units. And this is not a one-off. Like, it's always possible to build any matrix from a sum of the matrix units. Right? Like, this can always be done. Like theorem, if A is in Rm by n, then A is equal to the sum I equals 1 to m, sum j equals 1 to n of A ij Eij. Any matrix can be written as a linear combination of the matrix units, like this. And this is like actually very, very useful, as we'll see in certain calculations. So it's not just an idle curiosity I have here with this, all right? It's actually going to allow us to do some calculations that at the end of the calculation, you'll probably be like, what just happened? We could actually calculate that? Oh my goodness. But similarly, there's a theorem that if V is in Rn, then V is equal to the sum I equals 1 to n of V sub I, E sub I, right? You'll forgive me if I don't prove these theorems, but these theorems could easily be proved by simply calculating like the arbitrary component of both sides and showing that they have to be equal. We could just check that, both of these, the left-hand side and the right-hand side are equal component by component, and we'd have honest to goodness proofs of these assertions. But they're not especially, like, you probably believe it from these two examples, right? I mean, I would. Then again, I'm somewhat gullible, so. Let's see here. Oh, man. We will see that the matrix units and the standard basis are not disconnected in the sense that you can actually build the matrix units from appropriate products of the standard matrix. So there's like a whole set of interesting relations in terms of how to multiply matrix units by the standard basis and stuff. We will get to that. But before we get to that, we probably should be careful to define a few things. One of the things that's important for this course, of course, is the notion of linear combination, all right? So a finite R-linear combination, I can't spell, combo, there we go, of objects, A1 through A sub k, is a finite sum no E in sum. What's wrong with me? C1A1 plus CKAK, right? Which of course we have notation for, right? That's the summation I equals 1 to K of C sub I, A sub I, where the coefficients are what? They have to be an element of R, right? That's what makes it an R linear combination. If we're talking about a real linear combination, we would be using real coefficients for the linear combination, right? A complex linear combination would have complex coefficients. A rational linear combination, rational coefficients. A Z3 linear combination, Z3 coefficients, right? Period. And, okay, fine, for each I. We say the set containing 0 is formed by an empty sum. All right. And more generally, we talk about the span sub R of A1 through A sub k. This is equal to the set of all linear combinations. So we introduce span, and sometimes I sometimes capitalize span, I sometimes lowercase span. There's no significance to this. It's the same with like null and column. Sometimes I capitalize them, sometimes I lowercase them. I guess if I capitalize it and I'm like shouting column at you or something, I'm not sure exactly, but there's no reason. If you could explain the reason, well then, I don't know. You do better than me. Now there's one thing I left out on the board. The other important thing is if all of the constants are 0, it's called what? So if all the constants are 0, we have the trivial combination, right? You guys remember, perhaps, that plays an important role as we study linear independence, right? If you set a linear combination equal to 0, and it forces it to be the trivial combination, that means that that set's a linearly independent set, right? Now, we didn't dwell on that too deeply in 221, but it should have happened somewhere. All right. Great. Let's see here. So that brings us to something that's finally like, so far it's mostly just notation, right? There's nothing much that's been happening here. Matrix multiplication, though. Matrix multiplication. You know, you feel like you're really doing something once you do that, right? At least I do. Multiplication. I can't spell today. Multiplication. That's not a good sign. That is not a good sign. Goodness gracious. So we have A in our m by n and B in our n by p, let's say. Then AB is an element of what? R m by p, where AB, ij, is equal to the sum k equals 1 to n of a, I, k, b, k, j. So this right here is the definition of matrix multiplication. Now this is, of course, assuming that the result is actually a genuine matrix in the sense that it needs two indices, right? This definition has to be understood to have certain subcases, right? If the matrix multiplies to just give you a column, or if the matrix multiplies to just give you a row, then we can define it just in terms of a single index on both sides. If the matrix multiplies, if the two matrices multiply just to give you a scalar, there's no ij. It's just a number equal to a number. Yeah.
So for the column case, is that just a subcase of this definition, or do we need an entirely new definition?
Well, the subcase or not, it's defined in the notes. Here you go.
So you can just simplify the definition side instead of writing it.
Well, just to be on the safe side, I've explicitly put it in the notes. I was just trying to not write it, but I see that was a fool's errand. Let's see here. No, I'm just kidding. I usually write these down. X sub k I mean, that's a fair question. But that's how it works. If we had, like, this is a matrix column product, right? So here, like, A is in R m by n, and here X was in R n by 1 for this case here. And oh man, goodness gracious, you guys got to watch out for me if I don't move it. Oh well, sorry people at home. You guys are all here though, what do I care? Let's see here. So, like on the contrast, YB, the jth component of that would be like the sum over k equals 1 to n of y sub k b sub kj. So this is like a matrix column product, and here's a row matrix product, right? The answer being a column, the answer being a row. That's how the definition looks in those cases. And then finally, you can also have the case that you have like y is in R1 by n, and x is in R n by 1. In that case, you could calculate yx, and that would just be equal to the sum k equals 1 to n of yk xk. So there you go. There's like every contingency. All right. So genuine matrix it gives you a matrix. Matrix column gives you a column. Row matrix gives you a row, and finally, row times column just gives you a number, right? Now, a lot of times in like Math 221, we basically teach everything in terms of this, right? Because this is a dot product. That's what this is, right? It's a dot product of the row and the column. It gives us a number. And I mean, it's easy now that we have the right notation to identify that this product up here is exactly that dot product thing you were taught how to multiply matrices in 221, right? But we can connect with the row column discussion we had earlier today, right? So check this out, like AB ij is equal to the sum k equals 1 to n of a I k b k j. All right. So can you guys rewrite that in terms of like rows of A and columns of B? Isn't this nothing more than row I of A, the kth component of it, right? And what is this? This is column J of B, the kth component of it. You see? Going back to my definition of row and column earlier today. But what is this when we have a row and a column that are matched up like this, component to component? Well, this is what we define to be dot product, right? This is the dot product. This is row I of A, dot product with column J of B. Now, admittedly, from some pure perspective, this is a bit off-putting because I'm taking the dot product of like different kinds of objects, right? This is a row vector, this is a column vector. Can you take a dot product of a row and a column? Yeah, you can, just with the proper understanding that it just means this, all right? Which we could, of course, write in terms of like dot product of column with column, right? Like I could trade out, if you really must have columns, dot product with columns, then here you go. This column I of A transpose dotted with column J of B. There you go. Now it's all columns. You happy? It doesn't matter, right? We want to allow ourselves to take dot products of rows and columns with this understanding. It's helpful. And you were doing it in the last course anyway, right? So we have the dot product defined. Of course, the dot product can also be understood in terms of matrix multiplication, right? If we have V and W in Rn, than like v dot w, right? It's the sum k equals 1 to n of vk wk, right? Which you could also write as, you know, v transpose times w, right? Because that would make this, so remember this is equal to r what? N by 1. So the transpose of v is a 1 by n times a what? N by 1, right? Which is a 1 by 1. So this checks. So if we want to write dot product as a matrix multiplication, we can do that with transpose like such. All right. Now, there's more. So my real goal today is to show you some examples of, you know, oh man, are we already past time? But I said I'd go 1 minute over, right? So I said I'd go 3 minutes over, so I think I have 1 more minute I owe you 1 more minute. Oh, I'll behave. So next time we'll pick up here. Sorry, I seem to be a little bit behind, but hopefully that won't be a theme for this semester. See, I don't usually go over the syllabus. That was my stupidity. But I thought some of you guys had me before, so I probably should talk about it for a couple minutes.